All right. In this presentation, I'm going to be talking about sedimentary minerals and kind of summarizing the different minerals that you've hopefully read about in the textbook. So we're going to be going through kind of 7 to 10-ish minerals here. So again, these are kind of just the most common minerals that one would be encountering in sedimentary rocks. So we'll be going through ice, goethite, kaolinite, calcite, aragonite, and dolomite. You'll see why I've kind of grouped those together. Halite, gypsum, and then chert and agate. So just as a very quick refresher on sedimentary rocks, so these are going to be rocks that form via the accumulation or deposition of small particles and then will be subsequently cemented on the floor of bodies of water or at the Earth's surface. So usually sedimentary rocks are forming at the bottom of bodies of water. They can also sometimes form on the Earth's surface via other processes as well. So if you've taken Geo 101, you've seen this slide of sediment on the left, which is going to be made of loose fragments of rock that then get compacted and cemented together to form sedimentary rock over here on the right. So we would say that all of these kind of individual cobbles have been now lithified into a rock. And so in a lot of cases, sedimentary rocks are made up just of pieces of other rocks. And so in that case, thinking about what it means to be a sedimentary mineral gets a little bit complicated, because if you have an igneous rock that gets weathered into a nice roundish cobble, and then that cobble gets lithified into a sedimentary rock, are all of those igneous minerals suddenly sedimentary minerals? And so in this presentation, we are focusing on minerals that formed as a result of sedimentary processes, rather than minerals that are showing up in sedimentary rocks, but formed originally in an igneous or a metamorphic rock. So while if you look at sedimentary rocks, such as sandstone, for instance, is going to be made entirely of quartz, but that quartz has all come from previously existing igneous and metamorphic rocks. And so in general, we won't be talking about quartz as a sedimentary mineral, although we will be talking about chert and agate, which are very similar to quartz as sedimentary minerals. And so, as a quick reminder about the 4 main types of sedimentary rocks. So, our clastic sedimentary rocks are going to be the ones where you have those pieces of originally loose rock and mineral fragments that have later been cemented together. Biochemical rocks are going to be cemented together shells of organisms. So, all of the limestone that we have here in Kentucky is going to fall into that category. Our organic sedimentary rocks are going to be carbon-rich remains of once living organisms. So rather than being kind of the shells of organisms, instead we're thinking of kind of the guts of organisms, where only the carbon is left behind. So coal is going to be a good example of an organic sedimentary rock. And then we have our chemical sedimentary rocks, which occur when minerals precipitate directly out of water or via some other kind of chemical reaction. If you have a pre-existing rock that undergoes a chemical reaction, say with the atmosphere or with water, that can form a chemical sedimentary rock as well. And so in this lecture, we're going to be looking mostly at minerals that are forming in these chemical sedimentary rocks, because that's kind of the main category of these 4 categories where you're getting new minerals forming. In the case of clastic, biochemical, and organic, you're kind of dealing with pre-existing minerals that are just getting kind of smushed together. But in the case of chemical sedimentary rocks, you're actually forming new material and new minerals. And so when we're talking about sedimentary minerals, we're interested in those new minerals that have formed as a result of these chemical processes at the Earth's surface. So we're going to start with ice, mostly just again to make you all very unhappy about ice being a mineral, but recall that ice meets all of those four important criteria. It has a defined atomic arrangement and a definite crystal structure. It can be a solid at the Earth's surface. It has a definite chemical formula, and so it is meeting all of our criteria. And it's naturally formed. That's the other one. So again, if you're growing ice cubes in your freezer, that is not a mineral. That is a synthetic mineral. But if ice is forming naturally outside because it's cold out, then that is a mineral. And so I tried to choose pictures here of ice forming naturally outside, specifically in ways that make it look kind of like a normal mineral. Maybe the snowflake in the upper right is kind of, you probably haven't seen too many minerals forming like that, mostly because most minerals are not forming as they fall through the sky. But in all of these other cases, if I didn't tell you right off the bat that this is ice, you might believe it was some other mineral like calcite or gypsum or something that we think of as a kind of more typical mineral. So we've got a bunch of different habits that the ice is forming. We've got some stalactitic ice over here forming as icicles. We can see nicely in the case of this one in the top middle, the hexagonal symmetry of the ice. So that would be falling into our 6 over m, 2 over m, 2 over m Hermann-Mogen category. We see some kind of acicular ice in these ones over here. And then these pictures on the left are pictures that I actually took at England Falls last year during the winter when there were some just remarkable ice formations from the water that had frozen in that area. And there were actually kind of a spectacular different number of habits that you could see in the ice that had crystallized at England Falls. But I was particularly fond of this lower left one that actually shows a botryoidal habit for the ice that formed. So another important sedimentary mineral is goethite. So that OE, that's, it's a like German umlauty sort of thing, so it'd be like goethite. But if you're not very good at saying that, goethite is just fine. So this is, it's an iron oxide with a hydroxyl ion in there as well. And this mineral, like a couple minerals we'll see in this lecture, is an oxidation product. It's formed by chemical weathering of iron-rich minerals. So if you recall back to all of our igneous minerals that we talked about, a lot of them, especially things like olivine and pyroxene and amphibole, have a lot of iron in them. And that iron is often in the 2+ valence state, and when it interacts with the atmosphere, it's going to want to oxidize to 3+ iron. And so that is what's happening here in the case of goethite. So we know that oxygen has a -2 charge, and that OH group has a -1 charge, and so that means that this iron in goethite has to have a 3+ charge to balance it out. And so you see good examples of this on igneous rocks. So in this upper right-hand picture here, we're looking at a lava flow in Hawaii. So this lava flow gets its dark color from a bunch of pyroxene and olivine. But then this red color that we see in kind of this middle portion here is all goethite that has formed by the weathering of that original lava flow material. So usually goethite is going to be anhedral. It can range kind of from massive to botryoidal. So we've got some botryoidal cases down here in the lower left, to stalactitic here on the lower right. And in a lot of cases, it's just kind of looks almost like a stain or a kind of painting on the surface of the rock. So where the rock is in contact with the air, you're going to get very small amounts of goethite forming on that surface. So like most oxides, like you saw in some of the earlier labs, goethite is going to have a high specific gravity. It's pretty dense. And the main way to tell it apart from a lot of the other iron oxides, like hematite or magnetite, is by looking at the streak of the mineral. So goethite has a kind of yellowish brown streak, so it's a little bit less red than hematite and much less gray than magnetite. But like hematite and magnetite, because it's made up primarily of iron, goethite is mined frequently as a source of iron ore, so it's another one that we'll see a bit when we talk about economic minerals. All right, so our next mineral is kaolinite. It's got the chemical formula Al2Si2O5OH4. And so we have a silicate here, and if you look at that silicate group, we have an Si2O5. And so that, if you did the silicate mineral structures activity, you may remember that Si4O10 is kind of the ratio that we expect to see for a phyllosilicate. Since Si2O5 has that same ratio, that means that we are looking at a phyllosilicate here. So this is not a mica because it doesn't have aluminum in any of those tetrahedral sites, but it is part of that larger phyllosilicate category. So kaolinite is an example of a clay mineral. So these are minerals that are going to feel very much like clay on your fingers. They're going to be very crumbly, kind of make your fingers feel dirty. And the key thing about kaolinite is that it too, like goethite, is a weathering product. But in this case, it's forming via the weathering of feldspar. So you take feldspar that formed initially in igneous rocks, and when it interacts with the atmosphere or the environment, it's going to form this mineral kaolinite. And so I've got a chemical formula indicating that in the lower left here. So we have a formula for, say, a potassium feldspar in this first part of the equation, and we are adding a hydrogen ion here, and water. So essentially we're interacting feldspar with water, with slightly acidic water, and we're essentially switching the positions of that potassium and that hydrogen. And so what that means is that instead of having this hydrogen dissolved in the water, we end up with potassium ions dissolved in the water and some silicon atoms dissolved in the water and some hydroxyl ions that are built into that mineral structure. So we went from a mineral structure that had no water component to it to a mineral structure that now has a water component. And so that is this kaolinite, this clay. So you can see in the pictures in the upper right here, it's a very kind of white, light-colored mineral. You can see just how kind of crumbly it looks. So it has a dull luster. It's going to be anhedral in almost all cases. I'm showing this picture in the kind of lower middle here of a very kind of rare instance of euhedral kaolinite. because this is one of kind of the few instances where you can really convince yourself that indeed kaolinite is a phyllosilicate. It does have those layers, just the same way biotite and muscovite have those same layers. So even though you can't see that crystal structure in this massive anhedral case above, you can see it really nicely in this kind of rare example here. And then what we have in the lower right-hand corner here is what we call a pseudomorph. So pseudo meaning kind of fake or false, morph meaning shape, so we have false shape. So this is a false-shaped kaolinite. It sure looks very euhedral, but we've seen that if kaolinite forms euhedral crystals, it's going to look more like these layered structures to the left here. Kaolinite does not form these kind of blocky prismatic crystals, except for the fact that feldspar does form blocky prismatic crystals, as you've seen. And since kaolinite is forming from the weathering of feldspar, what's happening here is that you take a feldspar crystal that forms these nice prismatic blocky crystals, and you replace all of that feldspar material with this kaolinite clay material. And so the kaolinite clay material is just kind of taking on that shape that the feldspar initially had. It's being just kind of shoved into a crystal form that already existed. So it is a false shape in that kaolinite on its own naturally would not form that shape, but it is able, it's almost like it has a mold or a template that it's able to kind of fill in from the original feldspar material. And so this reaction of feldspar and water to form clay is really important, especially when we think about other planets such as Mars. So one of the things that the rover Curiosity has found on Mars is some of these clay minerals. So this is a headline from 2013 indicating Curiosity finding clay on Mars. And then this is a picture to the left that Curiosity took of a drill hole so it drilled down into the Martian surface. And identified clay in this rock. You can kind of see how crumbly and clay-like that material there looks. And so because these clay minerals, of which kaolinite is one, it's not the only one, but it's an important one, has these hydroxyl ions, that implies that there was once water on Mars, that these clay minerals could only have formed if there was once water to be interacting with minerals such as feldspar. So that's really important to understanding the past environment of Mars. Just as another side note, if you are interested in, say, ceramics or something like that, when you are sculpting things from clay, that clay is going to be made of these clay minerals such as kaolinite. There's kind of a whole field of understanding exactly which clay minerals you're going to want in different proportions in your clay that you're sculpting from in order to get sort of the properties that you want. So when we're talking about clay minerals, we really are talking kind of about what you picture in your head when you say clay. All right, so here we've got kind of three together: calcite, which we've already talked a lot about, but then also aragonite and dolomite. So all three of these are carbonates. That's why I've grouped them together. So calcite and aragonite are both going to be calcium carbonates, the mineral formula CaCO3. Dolomite is also a carbonate, but it adds in magnesium in place of some of the calcium. So rather than kind of having 100% calcium as your cation, you're going to have 50% calcium and 50% magnesium as your cations. And so looking at calcite and aragonite, these are what we call polymorphs. So the poly meaning multiple, morphs again meaning shapes. So this is basically saying these two minerals both have the same formula, but they exist in different shapes of that same mineral formula. So calcite is our more common example. That's why we've talked about it a lot already in this class. It tends to take on trigonal, which is a subset of that hexagonal crystal symmetry category. So it takes on trigonal or hexagonal symmetry. As we know, it's usually white to colorless, but importantly, I added in a picture here reminding you that it can take on actually a fair number of colors. It has rhombohedral cleavage and it effervesces easily. So those are kind of the main properties that you've learned for identifying calcite. Aragonite, in contrast, is less common. It can also be kind of white or colorless to tan. In most cases that you see it, it's going to have this tan structure. And the key thing that makes it differ from calcite is its shape. So it falls into the orthorhombic crystal class. And its habit often consists of these kind of radiating columns. So each individual crystal is fairly columnar, but all of these crystals meet at kind of a common midpoint and radiate outwards from there. A couple other kind of physical properties that distinguish it from calcite is that it has less evident cleavage and less evident effervescence. So it doesn't bubble quite as easily with hydrochloric acid. It will bubble a little, but not to a large degree. And so here I'm showing those crystal structures of the calcite versus the aragonite. So on the left here, what we're seeing in purple are these CO3 2- anionic groups. So recall, based on Pauling's rules, these end up in a triangular arrangement. So we've got one carbon atom in the middle of each of these triangles and then an oxygen atom at each vertex. And then we've got these octahedral sites that calcium is able to fill in. So we can see just from looking down the C-axis here, I believe, this rhombohedral shape. So this is from whence that rhombohedral cleavage comes. And so you'll notice here it also lists a couple of other mineral formulas. We've got siderite, FeCO3, magnesite, MgCO3, and rhodochrosite, MnCO3. And so each of those three other minerals is what we call isostructural to the calcite structure. So this isostructural is kind of the exact opposite of a polymorph. So a polymorph is when you have multiple shapes of the same mineral formula. Isostructural, meaning same structure, is when you have one shape for a bunch of different mineral formulas. So each of these different mineral formulas has the same structure, has these CO3 2- groups and these octahedral groups arranged in the same way. It's just a matter of what cation is filling in those octahedral sites. In contrast with aragonite here, we still have our carbonate anionic groups as triangles here. But now that the calcium, instead of being in these nice octahedral sites, if you look at this, say, in Crystal Viewer and you turn on ball and stick, what you'll see is that these calcium ions are cubically coordinated, so they have 8 oxygens that each one is attached to, but they're these sort of really awkward, distorted cubes. So they don't fit and form kind of perfect cube shapes. They're cubes where certain faces and certain bonds are longer or shorter than one another. And so you can see how these different crystal structures are going to lead to different symmetries. So here in the case of calcite, so if you imagine forming a rhombohedron, if you put 3 of those rhombohedrons together, kind of cyclically here, you would end up forming a hexagon. And so calcite is part of that hexagonal group. So you could imagine you'd have another octahedron here, another octahedron here, and another octahedron here to have a nice hexagon shape. Whereas here, in the case of aragonite, things are instead arranged sort of in rectangles. So we have a unit cell showing the kind of the repeating structure outlined in black here. So we have this repeating structure of 2 sets of calcium, 2 sets of calcium, and a carbonate and a carbonate. And so as with, say, Legos, you could just stack this rectangular prism over and over and over to create this aragonite structure. And so here we're going to be in the orthorhombic group, that 2 over m, 2 over m, 2 over m group. And so just to show, because this is going to become more important when we talk about metamorphic minerals, you may be wondering why the same mineral formula would form in 2 different ways, or what decides whether a bunch of calcium and carbon and oxygen is going to form calcite or form aragonite. And it's usually going to have to do with the external conditions that the mineral is forming under. And those external conditions are usually going to be pressure and temperature. So on the right now, I have what we call a phase diagram showing where these different minerals are stable. So we have pressure is increasing downwards. So that is representing going deeper in the earth. As you go deeper in the earth, you're going to higher pressures. The x-axis here is temperature. So as you go to the right, you're going to higher temperatures. And so what we see is that calcite is the mineral phase that is stable at low pressures, whereas aragonite is the phase that is stable at higher pressures. And so because us here on the Earth are existing at basically 0 degrees C and 0 kilobars of pressure, we exist in this stable calcite phase. And so that's why calcite is so much more common than aragonite, is that if you have a bunch of calcium and carbon and oxygen crystallizing together at the Earth's surface, you're going to form calcite. You have to get to these kind of slightly more exotic high pressure conditions before your minerals your elements are going to prefer to crystallize to form aragonite rather than calcite. Of course, that means if you do find aragonite in a mineral, it's telling you something interesting about the formation of that rock. All right, so the third then of those 3 important carbonates is dolomite. So this is where instead of having just calcium and the carbonate anionic group, we're adding in some magnesium. And so dolomite is very similar to calcite in terms of its structure and its cleavage. So you're going to see very similar habits. You're going to see that rhombohedral cleavage. It's often kind of a bit dirtier in terms of the colors it displays. So you can see here in these pictures, it often has kind of a pinkish color or a tannish color. It can be very nice and colorless, but it's a little less likely to be colorless than calcite. Calcite, of course, also can take on other colors, but it's more likely to be colorless. So that means that if you're looking at a single crystal, it's hard to know for sure whether you're looking at calcite or dolomite just from color alone. It's usually helpful to check the effervescence, so try to bubble some HCl on it Dolomite will bubble, it will effervesce, but it will effervesce a lot less effusively than calcite will. So you've seen calcite gets a pretty strong reaction with hydrochloric acid. Dolomite, you'll get a few bubbles, but it will be a lot less evident than with calcite. All right, so moving on to halite. This is one of the ones you probably already have a good sense of. So NaCl, we're just talking about salt here. This is a halide. Its anionic group is one of the halide elements, in this case chlorine. And so halite is part of a group of minerals that we call evaporites. We'll see another one in gypsum here in a second. So halite forms via the evaporation of water. So essentially, you have a whole bunch of water that's salt water. You have sodium and chlorine ions that are dissolved in that water. And if you evaporate that water, if you've got a little puddle of salt water and you evaporate the water out of that salt water puddle, the sodium and chlorine are going to stick around. They're not going to evaporate. And so eventually they will start to crystallize out to form minerals. And so basically every mineral that we made at the beginning of the term, when we made those borax or Epsom salt crystals, those were all evaporite minerals because we were forming them via dissolving ions in water and then evaporating out the water such that only the ions remain, and those ions then clump together and crystallize to form these different minerals. So halite has cubic habit and cubic cleavage, and as you saw in some of the previous labs, that stems directly from the microscopic atomic ordering of those sodium and chlorine ions. And of course, the most kind of diagnostic property of halite is that it has a salty taste. And so the pictures I'm showing here are showing well that cubic structure. I really like this picture in the bottom middle here because you can see all these kind of little like pits on the surface of the halite crystal. And so those would be places where the crystal has partially dissolved just a tiny little bit due to interaction with water, because of course halite is very water soluble. And then on the right here, this was just kind of a crazy picture I found of just how big some of these cubic crystals can get. So this is a salt mine. I forget what country it's from, but you can see the beautiful cubic crystals and just how gigantic they are compared to, say, a person. So here are kind of some more a little bit more interesting pictures of halite. There's kind of 2 points that I wanted to make here. The first relating to these pictures in the upper right is that halite not always colorless. It is often colorless or white, but it can take on these other colors if you have little bits of dissolved other ions in the crystal structure. So we've got a beautiful pink halite and a beautiful blue halite here. So if you get Himalayan sea salt, it's often pink, and that pink color is usually coming from little bits of iron and other cations that are kind of trapped within the structure of the salt. Interestingly, the pink color in this crystal that I'm showing here is not iron. It actually comes from little bits of algae and bacteria that got kind of trapped in the crystal structure as it crystallized. So if you see pink halite, you shouldn't necessarily lick it, because yes, it could just be iron, but it could also be bacteria. So in general, don't lick halite that you don't have a good sense of where it came from. And then what I really like, and maybe this is just because I'm a cooking nerd, is these pictures on the bottom here are an example of what we call hopper crystals. And these crystals are forming kind of as this picture in the top left here shows. These are crystals where instead of the whole crystal growing at the same rate to form these cubes, the edges and corners of the cube are forming much faster than the faces of the cube. And so you end up with these kind of inverted pyramid shapes that then, if you break this structure up, you end up with seeing that pyramid or portions of that pyramid, as is shown kind of here on the left. And so you get these really interesting kind of pyramid salt shapes. So these two on the left are nice examples of that pyramid shape. On the right here, you can really kind of see how the edges are growing more quickly than the middles of the crystals. And so if you like cooking and you've ever heard of flake salt or Maldon sea salt, these hopper crystals are that flake salt. So flake salt is flaky because it's bits and pieces of these kind of very thin hopper crystals that are forming. All right, next up we've got gypsum. This is another evaporite mineral, so another one forming via the evaporation of water. So if your water's got a bunch of calcium and some sulfate dissolved in it, then when you evaporate that water, you're going to be forming gypsum, which also then traps some of that water in the crystal structure. So gypsum, its cleavage can kind of vary, but usually it's good cleavage in one or two directions that often gives it a kind of silky structure. So this is a good example in the bottom right here of that silky texture on the sides of this gypsum crystal. It has pretty low hardness, so it's very easily scratched. You'll also frequently see references to selenite or satin spar. These are both forms of colorless transparent gypsum. So like we're seeing here in this bottom middle or here over to the right. And gypsum also has a fair number of economic uses. One of the main ones is it's used in the production of kind of stucco or wallboard for construction purposes. And so here's just some more pictures of some of the habits and colors that gypsum can take on. So it's usually colorless and fairly translucent, so it's going to be most commonly mistaken for things like calcite or halite, which are both also have kind of similar cleavage. But so you're really going to be looking for that, how easily scratched it is, the very low hardness of gypsum, and how well developed the different cleavage planes are. So the silky texture is very indicative of gypsum rather than something like calcite or halite. On the left here, we have what are called desert roses. So these form in the desert where you have a bunch of sand. That sand often has some kind of oxidized iron, giving it a reddish brown color. And if that sand gets trapped in the crystals as the crystals are growing, you end up with kind of sandy brownish crystals that often form these clusters that have an almost kind of a flower-like shape to them. Again, in the bottom right here, we can see just how big some of these gypsum crystals can get. So just like with the halite crystals, this is kind of indicating that evaporite minerals can get very big if you've got a lot of ions precipitating out of a lot of water. So these ones then in the bottom middle here are called selenite wands or gypsum wands. They have an almost kind of fiber optic effect where you have this long kind of stringy, silky habit on the side, but you can look straight down the mineral and almost kind of see straight through it. Okay, and so to finish up, I think we get to finish up here with the most fun one, which is chert and agate. So chert and agate both are just silicon dioxide, same mineral formula as quartz, same mineral structure as quartz on the microscopic level. But the difference is that on the macroscopic level, these are what we call microcrystalline or cryptocrystalline, which means that they are masses of millions upon millions of tiny, tiny, tiny little quartz crystals. So you would never see with the naked eye any of, say, that prismatic crystal habit you're used to seeing with quartz, because the grains are so tiny that they end up having this kind of massive, compact habit. So if we looked at these under an optical microscope or under the benchtop SEM, you would be able to see that indeed there are individual crystals in there, but they're so tiny that we can't identify them. So the differences between, you'll see words such as chert or agate or flint or jasper. Those are all referring to these micro or cryptocrystalline forms of quartz. There is not sort of a perfect way to distinguish between each one of those. They're often used interchangeably. Chert in general is going to have this compact state of aggregation. So chert, here we're looking, the bottom left and bottom right are both examples of chert. So it's kind of just also just super pretty. So this is just a gorgeous piece of agate for you to feast your eyes on here. Oh, I got this from the Wikipedia page, but this is from Mexico. You can see its size compared to a tennis ball. And just all the incredibly beautiful banding that's going on all around this very complicated mineral structure. So I think this is a type of agate called a crazy lace agate. You can kind of see it's got a lot of kind of lace-like parts, but it is also pretty crazy. And another slide here, just of some beautiful different types of agate. So agates often get names, kind of distinguishing them based either on where they formed or what kind of other minerals they have worked into them. So for instance, this dendritic agate has dendritic manganese crystals that were kind of trapped within the crystallizing quartz. So these are some just very beautiful examples, but all of them kind of share that same feature of being banded and having formed via filling in these empty spaces in other rock. And of course then, you couldn't leave without talking about Kentucky agate. So Kentucky agate is the state rock of Kentucky. Despite the fact that it is not a rock, it is a mineral. In contrast, the state mineral of Kentucky is coal, which is not a mineral, it's a rock. So our state rock is a mineral, and our state mineral is a rock. Clearly, nobody consulted with geologists before making these distinctions. But Kentucky is actually pretty famous in rock and mineral collecting circles because of the really beautiful agates that we can find in the creeks around here. So you can see the beautiful red, black, and gray banding in the structure here. It's that red color that makes Kentucky agate special. That's kind of what's especially prized by mineral collectors. And so I'm showing here some beautiful, very close-up pictures of Kentucky agate, showing those red layers and how those red layers consist of lots of tiny, tiny, tiny little droplets. And if you look chemically at the composition of those droplets, that's what this chart in the lower right is showing. So you have the color of the banding is what these rows are, and then the elements, just like we looked at on the benchtop SEM, shown here in the columns. And so it's oxidized iron that is giving the red agate its red color. You can see that the red agate has a much higher percentage of Fe2O3 than any of the other colors of agate banding. And that makes sense since Fe2O3 is the mineral hematite, and we're used to seeing a very, very red hematite. And so you could start to look at these different bands to try to figure out kind of what color is formed by which elements. So, for instance, this dark blue agate seems to be has a lot of calcium. That's actually a very large amount of calcium, and a fairly large amount of manganese as well. Whereas in all of these other cases, it's really just trace amounts of elements that are causing the different colors that we see. This is also a nice example, I think, of kind of the difference between that kind of normal crystalline quartz and the micro or cryptocrystalline quartz that forms most of the layers of an agate. But here you can see we have some layers that actually are actually crystalline. You can see the crystalline structure of the quartz here, whereas if you move to these other layers, the crystals again become so tiny that you can't distinguish them from one another, even on this fairly zoomed in scale. So this would be another really cool thing to put on the benchtop SEM and start to see whether we could see the difference in the banding based on the chemical elements present, and whether we could zoom in far enough that we would start to see the tiny, tiny crystals that are making up these bands. And so, just to finish up here are some beautiful pictures of Kentucky agate. Of course, not all of them are going to be quite as spectacular as these examples, so I included in the middle here kind of an example of what you'd kind of be more likely to find if you're going through creeks and cutting open geodes on your own. It is still beautiful in its own way, for sure. There's also, Kentucky has a Kentucky Agate Festival, or it's part of the Mushroom Festival. It's held in Estill County every year in April. And so if all of this chaos had not occurred, we could have gone to the Kentucky Agate Festival, which I think would have been a lot of fun. So hopefully in future years we'll be able to do a field trip along those lines, and maybe also a field trip at some point just poking around creeks and trying to find some of these agates and geodes to cut open. So that's it for sedimentary minerals. Please let me know if you have any questions. Get those reading questions answered. And if you are interested in trying to keep up with the microscope side of things too, there's some reading on Moodle for the microscopes. And hopefully within the next couple days here, I'll have a couple lecture slides online about microscopes as well. So talk to you later. Bye.